Hi everyone! In this video we are going to see how we can simulate the solar system using the actual Newtonian physics, Tensorflow.js, and at the end we are going to use React to render a 3D model of the solar system. But before I get started, I would like to briefly go over the theories. In order to simulate the solar system, we only need to consider the gravitational interaction between the bodies in the solar system, which is the planets and the sun. And for that, we can use Newton's gravitational equation, which is F equals g m1 m2 over r squared. But that is the scalar form of this equation. There's another form, which is the vector form, and that is what we are going to use today for our code. So in order to determine the position of an object, we can just use this very simple equation, which is v times t. But to simulate something, we basically need to know where the object will be in the future. Mathematically, that means we need to know its position at time t plus delta t. Given that we know its position at time t, we can say its position in the future will be its old position plus v times delta t. And delta t is a very small time step. And similarly, we have another equation for velocity. And this entire method is known as the Euler algorithm, which is derived from his numerical method for solving first-order differential equations. Now, in order to calculate the acceleration, we can use Newton's second law of motion, which is F equals ma, or A equals F over m. And the only force that we are going to take into consideration for our code is the gravitational force. So we are going to use that to determine the acceleration. So we can say the acceleration of planet J is the sum of forces exerted onto it divided by its mass. And that's pretty much it for the theories. Let's get started and do some coding. Okay, I'm just going to use Code Sandbox, which is a free online code editor, and it comes with a variety of useful templates. For today's video, I'm going to use React and Rect3 Fiber for making a 3D model of the solar system, and TensorFlow for doing the mathematical calculations. And you can see how easy it is to add an NPM dependency using Code Sandbox. Now, the next thing that we need to do is to import some initial data about the solar system. And I have prepared that in the JSON format. And I'm just going to drop it onto my project. And you can see there's a list of all the big masses in the solar system and their data, like their position, their initial velocity, mass, radius, and the color associated with them. And there's also the gravitational constant. Our length unit is the distance of Earth to the Sun, and the time unit is the day. Okay, so first of all, we need to import TensorFlow, which we are going to use for every mathematical operation. And then we need to import the data from the JSON file. And now let's define a variable number of planets, which is the size of the planets array. Let's just extract the positions array from the planet's objects. And we get planet.x. And we need to do the same thing for the velocity. And we're just going to call it v initial array. It's the v property. And we also need to do the same thing for the masses. And we get the m property. Now, in order to use TensorFlow, we just have to make a tensor copy of all these data. So I make a two-dimensional tensor from this array with shape of number of planets by 3. And again, we should do the same thing for the velocity. And we also have the gravitational constant that we have to convert to a scalar tensor. Now, I'm just going to create a new component called solar system. And let's just render nothing for now. And I'm just going to add an element of it to our app component. Now the fun part, that is calculating the acceleration. So acceleration is a function of position, but before using the positions tensor, we have to unstack it. Because we cannot loop over a tensor, we have to convert it to a list of one-dimensional tensors. Now I'm just writing the part that we calculate the sum of the forces. I don't want to calculate the same force twice, so I just make the second loop start from I plus 1, and when we did the calculations, we just add the force to the planet J as well. Now let's just extract the position for planet J, like so. And let's do the same thing for planet I as well. We can just move it to the outer loop. The force tensor is equal to G multiplied by mass of planet I multiplied by mass of planet J. What's the error? Divided by r to the power of 3. And r is the distance between two planets. And first we just need to calculate the vector by just subtracting position of planet J and planet I, and we can just calculate the norm of the vector. Now we need to store these forces somewhere, so let's create a list of one-dimensional tensors. So we basically store every planet's acceleration as a one-dimensional tensor, and we initialize it with 0 for every axis. So as I said, I'm just going to add this force to planet I, and the same force but in the opposite direction to planet J. So I basically add it to acceleration for I, and I subtract it for planet J. But this is the force, not the acceleration. So at the end of the outer loop, we just divide this number by the mass of planet I. So that way we have the acceleration. Cool. Now we have a list of one-dimensional tensors. So we just have to convert it to a two-dimensional tensor. For that we can use tf.stack. Now I want to check if there's any errors in this function. So let's create a callback and call it compute using use callback. So we memorize this function and say const a equals calc a given the initial positions tensors. Now I use the print method to print it, and I just call it inside the render function. And we have something in the console. There we go. Now let's remove this line. And let's store the current position using useRef. The reason I don't use states here is because I don't want to trigger a render whenever the value changes. And I do the same thing for the velocity. Now it's time for the second fun part, that is determining the new position, which is the old position plus the old velocity times delta t, but I don't have the delta t tensor yet. Let's take it as a prop and memorize it. So we add a new prop called dt, and default value would be 0.1, and I memorize it like so. tf.scalar dt, and whenever dt changes. It seems that it wasn't auto-imported. So, come on. There we go. Alright, let's continue with the new velocity. new v is equal to old v plus a times dt. And since TensorFlow uses WebGL for its backend, we have to explicitly release the memory since it doesn't use JavaScript's memory management. So we have to wrap everything inside tf.tidy, and we can return the tensors that we need, like so, and use the returned values. So let's replace the current position with the new position and the current velocity with the new velocity. Cool. We should also dispose the previous position and the previous velocity because they were defined outside the scope of the tf.tidy callback. Alright, before I use these values, I have to convert them to JavaScript arrays. So I can use the array method, which returns a promise, and when the promise resolves, I can have access to the actual JavaScript object. Now this is what I'm going to use state for. So I just define pose and initialize it with the initial positions array, and we do set pose whenever the new position is ready. Now let's actually render something, and in order to do that we need to import canvas and use 3 from React 3 Fiber. Then I just wrap the solar system component inside canvas. And instead of null, let's just render something. I start with a group element, and let's add an ambient light and a point light. And then we render the planets, and we map the pose array and return a mesh for each planet, and every mesh requires a geometry and a material. And let's just add a key because it's a list, and we need to attach the geometry to the mesh. So we say attach as the geometry, and we need to attach the material as well, and we attach it as the material. And we basically need a sphere for the geometry, and Three.js already comes with a sphere geometry element, and we can use that. And it takes 3 arguments. The first argument is the radius, and the second and the third arguments are the segments. And for the material, let's use mesh standard material. And we can add the color to the material, and we can use the color from the JSON file. It's not rendering anything, so let's add some styles just to make sure if the canvas is being rendered. So add a background color. It's being rendered, but it's very small, so let's add height to it and remove the body margin. Still nothing. So let's just change the position of the camera. Let's just move the camera 20 pixels, 20 units away from the origin. Still nothing. Let's just reload the page. What the hell? Maybe adding a new control would fix it. Let's just use orbit controls, import it from 3 examples, and we're going to need the extend function to add this new element to the supported elements of React 3 Fiber. And we're going to use it like this. So we add a tag, and this element requires the camera as an argument. So we can just extract the camera from use3. There we go. We got the sun. Yay. But we only got the sun. Let's just use the actual radius. Oh, it's too small. Let's multiply it by 1,000. Probably the sun's to all the other planets. That's weird. Where are the other planets? Let's try 50. Okay, let's say if it's the sun, use 0.2, otherwise use the actual radius multiplied by 500. What? It was replaced by Jupiter. Oh, I forgot to add the position to the mesh. Sorry. There we go. Yay! We also got these nice orbit controls. We can move the camera, we can zoom in. Alright, now let's add some dynamics. Now I guess if we continuously call the compute function, we can get all the planets moving. So let's just use useEffect and call compute inside request animation frame. And add pose as a dependency because we only want to do computation whenever the position changes. And dependencies for the callback. And I just noticed that I forgot to update the positions argument for the calc_a function. And it's still complaining. I forgot to add dt_tensor as a dependency. Alright, cool. Let's just zoom in and see if the planets are moving. Why is Mercury escaping from the solar system? It must be something inside calc_a. Oh, I forgot to multiply it by the vector. Let's check again. Awesome. So they are orbiting around the sun. Let's make the planets a bit bigger. Check again. Isn't it cool? I'm just gonna move the camera a bit forward. So for the last thing, I would like to visualize the trajectory like a line or a tail that planets leave behind. And for that, I just copy this code and replace mesh with line, and change the key. And line doesn't need position, and we don't need sphere for the line. Need the basic geometry, and for the material, let's use basic line, or sorry, line basic material. And let's leave the color. And for geometry, we need to pass an array of vertices. And so far we only have the current position, but for this tail we need a series of positions. So let's create a new state and call it traj, and initialize it with initial traj. Initial traj is basically a list of positions for every planet. So we can map initial positions and create an array of size 20. Let's say we just only store 20 points. I think we're going to need this number later on, so let's store it in a variable instead. And call it traj size and use that. Okay, so whenever we have the updated position, we want to add it to the trajectory. So we do set traj.map. So for every planet we update its last position, and we make sure not to change the size of this array. So we slice it and at the new position. And I need to add the index. Alright, so let's use this variable for rendering the lines. So I replace it with traj. What happened? Traj.map. And pass the points to the vertices. And for that, we have to convert the JavaScript array to 3JS vector. Like that. And let's see if it's drawing the line. It's not, because whenever we update the vertices prop, we have to tell React3 Fiber to update the 3JS object. So let's add a new callback and call it handle update geometry. And add an empty list as a dependency, and we basically need to set vertices need update to true in the object that is passed to this callback. And there we go, we got the tail as well, but it's kind of short. It's because of the traj size, or we can alternatively skip a few time steps, and for that we are going to need the number of time steps that has been passed, and we initialize it with 0, and we say if the number of time steps we increment it if is divisible by 30, set the trajectory. Okay, still the same. Let's change it to 40. Never mind, I forgot to compare it with 0. And let's check it again. There we go. It's so awesome. I'm really excited. Let's see a separate tab. So cool. We have the sun, Mercury, Venus, the Earth, Mars, Jupiter, Saturn, the next one, and Neptune and Pluto. I don't know. I hope you enjoyed this video. See you in the next.